Right, so we got cut off rather unfortunately, and so this discussion should be treated as a continuation of the last video, and I'll sort of name or number the videos to make that more apparent. But here it may be better not to start all over again, but just to continue. However, let me at least restate this theorem, which is, suppose f is bounded, continuous, concave, differentiable, and gamma is non-empty valued, compact valued, continuous, and convex. Suppose x tilde star is feasible starting at x naught. Always the states lie in the interior of feasibility, and x tilde star along its entire path satisfies all the Euler equations. In addition, suppose transversality condition B is satisfied, which says the limit of this discounted value beta to the t of the increment on the return function if the current state is incremented a little, right? Essentially that times the change in the current state. Suppose that is greater than or equal to 0 in the limit, then x tilde star is an optimal plan. And what we were saying is that we can interpret along any feasible path the discounted present value, or the limit of the partial sums, to be a sum of discounted present value along the path x tilde star that satisfies the Euler equations and transversality, plus a dt given by the sum of these two terms. And we said that if we do a little bit of rearranging, then everything but the last term vanishes because Euler equations are satisfied along the path x tilde star, right? And the last term can be written as this discounted term, right? So if transversality condition B is satisfied, which is here, that the limit of this discounted term is greater than or equal to 0, that implies that the limit of the negative of this is less than or equal to 0, right? So what we are saying is that any other feasible path here is less than or equal to the sum obtained from the discounted present value along this feasible path which satisfies the Euler equations, right, plus this last term. And this last term is something which is less than or equal to 0. Right? But that means that any other feasible path must give a discounted present value which is less than or equal to that given by x tilde star. So x tilde star is optimal. Right? So, here is a sort of interpretation of this transversality condition. The condition is, so if I remove the, it doesn't matter whether it's a t here or a t plus 1. So if I just say beta to the t, f1 x star t x star t plus 1 times, or if you wish, dot, if these are, well, if these are vector derivatives, right? X sorry, yeah. The transversality condition is that this be greater than or equal to 0, translating into that the negative of this be less than or equal to 0, right? So the interpretation often given is that how do you improve upon the path x star tilde, if at all, right? So that starts at x naught, goes to an x star 1, x star 2, etc., x star t, and this t goes to an infinite horizon, right? So one way to improve is to see whether you can do something locally at, let's say, some xt plus 1. Is there some local xt plus 1 that where if you deviate from x star t plus 1 you can get some higher utility? And you see that those are precisely the things that the choice of x star t plus 1 doesn't allow you to do, because those are chosen using the Euler equations. The Euler equation is saying that, if I play around with the xt plus 1, I'm not going to get any local benefit either this period or next period, right? The sum of those benefits is equal to 0, right? So then what can I do to get any benefit? So possibly I can do something at the horizon t, right? And in an infinite horizon problem, that means that possibly I can benefit as the limit of t goes to 0, right? So I can't benefit locally because the Euler equations are satisfied. Maybe I can benefit in the far horizon, right? So the transversality condition says, rules that out, that I can't benefit in the far horizon, right? So one way of looking at this condition is to interpret the states as sort of capital stocks in an optimal growth kind of problem, right? So what you're saying is that you can't have, so you cannot have a feasible path x tilde starting at x naught, such that limit of this is negative. That is being ruled out, that the limit of this is negative. So what is the limit of this anyway? So, at a far horizon t, suppose instead of x star t, you were to vary that to some xt with some delta, right? If you could make this limit negative, that's saying something like that in the far horizon you can vary your capital stock so that when you evaluate the value of the capital stock in the far horizon, you can decrease it, right? So what's being said is that the path is optimal because you can't decrease the value of the capital stock in the far horizon. You've already exhausted its value along the time that takes it for you to hit the far horizon, right? So maybe at this point of time, it may be good to sort of take another attempt at looking at what, well, either the Euler equations or dynamic programming is saying here, and how the sort of far horizon enters. And maybe the dynamic programming setting makes this slightly more transparent, especially with the exposure you've had earlier in other courses, not in macro, but in other courses. So let me try and do a little bit of that. So let's say the current state is x naught. I can start at any period t, but let me start at 0 and say the current state x naught is given, right? And this is just a small example. So I have a choice. The decision maker has a choice. Say a two-way choice. There are two feasible states, x1 and x prime 1. Okay. And if I choose x1, let me come to the returns later. So I choose x1. From there, I have some feasible choices. From these, I have some other feasible choices. Yeah, and life goes on, right? And so in dynamic programming, you're sitting at the current period. Let's say if it's period 0, you're sitting at x naught and thinking of whether to choose x1 and x1 prime, right? Suppose you've already thought of how to make the future choices from there, how to make them well, yeah? And let me call those choices of future states using these arrows here, okay? So these look, well, like a game tree. It's a decision tree, right? And these branches and twigs look like histories, but this is a simpler problem. So everything in a history is encapsulated in the current state, okay? The current state here, here, etc., etc. And so suppose you've made those choices, right? And here you're at x1, and so what you'll get from these particular choices, suppose it's v star 1, v star x1. You don't necessarily interpret it as a value function, but that's what essentially we're going to do. And here you'll get a v star x1 prime. So you're sitting here and thinking, well, if I choose x1, I'm going to get a total payoff of f of x naught x1 plus beta times v star of x1. And here I'm going to get, if I choose x prime 1, I'm going to get f of x naught x prime 1 plus beta v star x prime 1, right? So in dynamic programming, at this state x naught, but also at the state x1 here, at x prime 1 here, at whatever states here, etc., right? The dynamic programming choice in the Bellman equation is which of these, which is higher, right? It's a local choice. At any state, it's the choice saying, at this state, at x naught, which is my best available choice, okay? And you're saying that, look, under certain conditions, I have that the optimal choices, the optimal plan, right, and the optimal value function satisfy this, that at every state, called the state x naught, it must be that whatever I get, the payoff that I get there, it maximizes just this, the current reward, future reward using v star, right? I'm maximizing this. So in other words, what are you doing? You're saying that if you're at an optimal plan, right, then there is no state where you can do better by just deviating from your chosen your chosen control or your chosen state there once. Okay, you can't do better by deviating once at x naught. If you've chosen the max of these two, you can't do better by one deviation here, given your choices and the values starting here. Similarly, if you're here, you can't do better by moving from here to here, given your choices here, and so forth. Okay? So dynamic programming is saying that the one deviation principle is necessary and sufficient to characterize your optimal plan. Okay, so in the background is some kind of transversality which is lurking, which is saying that if you can't benefit using a finite horizon of deviations, yeah, then that translates into something equivalent which says you can't benefit from a single deviation, right? And lurking in the background is that the infinite horizon doesn't get you any value. Okay? If we look at, so I don't want to come back to transversality with the Euler equation, but if we look at these transversality kinds of conditions, so they're sort of saying that in the infinite horizon, you shouldn't be getting any value, right? From whatever, if you interpret the state as a capital stock, from whatever capital stock you have. So you shouldn't be, it shouldn't be that you have a positive value there and you can change this to decrease the value there and eat that value in the finite horizon. That you shouldn't be able to do, right? So the question may arise, why in the infinite horizon should you keep any capital stock at all? Why not just eat all the capital stock? And in some problems that could be happening. In other problems, maybe you can't eat the capital, so maybe it's not a one sector model where you can eat all the capital at once. So what could be happening in other models that, the dynamics say that you accumulate lots and lots of capital, and then in the infinite horizon, you can't bring it down to zero because there is some rate of depreciation that puts a bound on that, right? But it shouldn't be that you get any utility from that, okay? All right. So there is this little section which, right now doesn't seem to actually warrant much time. You would have in your studies of macro, you would have come across this assumption of no Ponzi games, and it's being flagged here because sometimes the no Ponzi game assumption looks like it's a transversality condition, but it isn't. It's coming from a different context. And that context is basically how, especially in macro, but even more generally, how general equilibrium and the machinery of the general equilibrium framework is implemented and interpreted, right? So if you were to look at, a standard Arrow-Debreu treatment of general equilibrium, right? So, so by an Arrow-Debreu treatment of general equilibrium, I mean that the horizon, it's not necessarily a static model. The horizon can be long, it can be finite, it can be infinite horizon, right? But the interpretation there is that you make, as a decision maker, you make all your choices now. Okay? In the optimization problem that we've been talking about as the sequences problem, we're also doing that, right? We're making all our choices now, at least saying that, well, when we say we're making all our choices now, I'm saying that I know how best to choose at every state, right? So then, in some sense, I know what optimal action I'm going to play in each time period, yeah, as a function of the state there. So it's a dynamic horizon, but the choice is static in that sense, right? It's just in game theoretic terms, the horizon is dynamic, but the choice is a static choice of strategy, right? It tells you what to choose in game theory at every history. Here, things are somewhat simpler. Histories are described completely by state, so it tells you what to do at every state, right? So, an Arrow-Debreu general equilibrium is something like that, where people choose. Let's take the consumption problem of households in Arrow-Debreu, right? So consumers choose what to consume at each time period. If there's uncertainty, they choose what to consume at each dated event, time period crossed with state, realized state, right? But the apparatus, or the way to think Arrow-Debreu, is to say that all the markets for the commodities open at time t equals 0. Okay, so all the trading takes place there. But what is the trading? It's each market, an equilibrium price vector has a price for each of the markets. So suppose there's no uncertainty and there's only a single good. Then there's a market for that good at time 0, time 1, time 2, time 3, etc., right? But all those trading in all those markets open and close in at time 0. Okay, so there's a price vector, there's a price for the good at time 0, good at time 1, etc. All the trades happen now, and there's some mechanism in place that enforces the trades in future, right? So if I have paid 2 rupees to buy 3 units of consumption at time 2, there is some mechanism that will actually enforce that the guy who has promised to deliver 3 units of consumption to me at time 2 will in fact do so. That's Arrow-Debreu. So when we write down the Arrow-Debreu problem for a consumer, it looks something like this. So suppose the consumer at each time t is endowed with the same W units of the good. Okay? It doesn't matter if this varies. If it's WT units at time t, nothing will change, except that well, I'll come to what will change. So suppose a consumer is endowed with W units of the consumption good at each time t, right? And at time t equals 0 maximizes this discounted present value. Yeah. All the markets for consumption at any time t open and close at time t equals 0, and the price of consumption of the tth period good is pt, right? So then the budget constraint that the consumer faces is summation ptct is less than or equal to summation ptw. It's a single budget constraint. So it's like saying the consumer can sell his or her endowments at that he or she will have at every time now at time t equals 0, get that income and buy a consumption plan CT over time now, okay, subject to feasibility, right? In this particular problem, you can see, well, so let me backtrack a little bit. Suppose the prices turn out to be PT is equal to beta to the T, right? So don't ask me why, but you must have encountered this earlier in your macro also. Suppose the prices are PT equals beta to the T, right? So, and if you were to write down the Lagrangian for this problem, it'll be something like that plus, let's say I ignore non-negativity here because this is nice, strictly increasing, strictly concave, etc. And it meets in other conditions, so you don't have zero consumption. So I have something like summation PT, and I'm hoping that everything is nicely defined. You know, these infinite series are all nicely defined, right? So suppose this PT is beta to the T, then my first order conditions will look like beta to the T U prime of CT minus lambda is equal to 0. So that will say that my consumption will not vary with time, right? It will be C, some C for all T, right? And you can see that because the budget constraint looks like that, well, why not rewrite it even further? So let me say WT, W, right, minus summation C, right? I don't want to waste any amount of my income, so I'll set that equal to 0, so C is equal to W. You know, that's my solution. So this is a little distracting. I didn't want to talk about the solution. You know, if instead of a constant W, you have different amounts of endowments, but if PT is equal to beta to the T, then it will still be that your consumption is the same over time, right? And this is just because you're trying to sort of spread your consumption, right, because of diminishing marginal utility. But then, you know, if this is WT, then your C will not be equal to a single W, but it will be equal to the discounted present value of income. And you can show that, right? So, so the discounted present value of consumption will be equal to the discounted present value of income, right? So it'll be something like this. So that's equal to that, which is equal to that. So yeah, it's something like a permanent income kind of model, right? A particularly simple one. Okay, so now, you know, that's Arrow de Bro. But what happens if that's not how things work? So first, you know, Arrow interpreted this to say that, look, if I change everything by saying that, look, at time t equals 0, I cannot trade in all the markets, but I can trade the unit of account in each market, right? So nothing changes. So he showed that, the budget sets of the consumers in particular will be the same in Aerodebro as in something like that. And then, work by Radner and then others started with more sort of restrictive assumptions so they could deal with dynamic programming, with dynamic models in a more natural way. So what Radner started was, well, what happens if instead of Aerodebro, I have something where, let's say, simple problem, the worker or the consumer is endowed with nothing to start with, some asset stock x not equals 0. That's just to associate it with the Aerodebro's specific example that we were working with, right? And then this worker will be endowed with some amount of the good, same amount of the good, W in each period. In addition, the worker can borrow or lend at some interest rate R, okay? And now, in particular, that interest rate satisfies that 1 plus R is equal to 1 by beta. If I make this assumption, there's a correspondence with the assumption earlier that the Aerodebro prices are PT is equal to beta to the T. Right? Because in both cases, with 1 unit saved today, I can buy 1 by beta units tomorrow. Okay, so here the price is 1 today of the single unit and it drops to beta tomorrow here. So I can buy 1 by beta tomorrow. Here, with 1 unit saved today, if I lend that and I get an interest rate according to this formula, right, then tomorrow I'll have 1 by beta units and I can buy 1 by beta units tomorrow, right? So with this sort of 1 period bond available to me to sell or buy, I can formulate the maximization problem as a sort of sequences problem that we've seen earlier, right, in the optimal growth model, accepting that here we have a slightly different thing here because the consumer can accumulate some capital or accumulate some debt. Okay, so here, these now are intertemporal budget constraints, today and tomorrow. And we've seen this kind of budget constraint in earlier examples, so you can take a look at that. Right? I can replace the 1 plus R times xt with xt by beta. And then I can multiply, so let me try and bring both things together on the same page. So I have CT is less than or equal to W plus xt by beta minus xt plus 1. It's the same constraint. And then I multiply through by beta to the t. So I have beta to the t CT is less than or equal to this. And now if I take partial sums adding from 0 to capital T, right, then you will notice that, these things will cancel out from one time period to the next one. Yeah, you can do that and check. So my sort of budget constraint for the first T plus 1 time periods will be discounted present value of consumption is less than or equal to discounted present value of income minus beta to the T times my asset stock or my debt stock. Okay. So to make this correspond to exactly the Arrow-Debreu problem. I want to remove this. So I can remove this by saying that in the infinite horizon, this limit goes to 0. That's the no Ponzi game condition, right? So in particular, assets are, that's asset, and this is debt, right? So in particular, you know, if I have debt, then in some sense I'm adding to my income, right? In the sense that I can consume by borrowing. Okay, so this says that in the limit I should not be able to do that, right? In the limit I should not be able to carry any value of debt. Yeah, so I can't play a Ponzi game. Like, I don't know whether it happens in your part of the country, but the part of the country that I, well, sort of come from or came from, or where my near ancestors are from, which is in the East, Ponzi games happen quite a lot. Right. Not so much by consumers, but by sort of, quote unquote firms, not even fly by night firms. They keep flying for maybe 20 years and then disappear. Okay. So what happens if returns are not bounded? So I want to just touch upon a theorem in Stokey, Lucas, and Prescott, which says, suppose the environment satisfies assumptions 1 and 2, and T is the Bellman operator. And suppose, returns may not be bounded, but suppose there is some sort of value-like function v hat, which satisfies that T v hat is less than or equal to v hat. Okay. And for this value-like function, there is some transversality kind of stuff that's happening. Okay. And in addition, for this value-like function, starting at any x naught, right, for all feasible sequences, the discounted present value of the sequences problem is less than or equal to what v hat of x naught is. Right? So if these three assumptions are satisfied, then it's easy to see that there is a limiting function v of x that we get by repeatedly applying t to this value-like function v hat. Okay, and the theorem says that this is a fixed point, and this function v is actually the value function of the sequences problem, right? So please notice that the Bellman map we've shown earlier satisfies monotonicity, right? So if there's a function v hat that satisfies assumption 1, then this is true, and then I can apply t to both sides again, right? So if I apply t to both sides, and since t is monotone, this side is t of t v hat, right? Same as t2 v hat. Then that must be less than or equal to t v hat, right? And similarly, applying it to both sides again, I get that t3 v hat is less than or equal to this. So if I start with a v hat, by the way, these inequalities are all interpreted pointwise, so at every x, right? So I start with a v hat, right? I'll have a decreasing sequence at any x, right? And we know that a bounded decreasing sequence will converge to its infimum. If it's not bounded, it will converge to negative infinity. Whichever it is, if I can define my v function on the extended real numbers, I'll just say that this v function exists. Okay? It's the limit, right? And the theorem says that this actually will be the value function. Okay, so here is an example where the boundedness condition is met. It's also true that in the examples, effectively I can put an upper bound on the amount of capital stock that it will be sensible to have. Okay, and if I can put an upper bound on the sensible amount of capital stock, I have effectively bounded the entire problem. And I think this is also part of problem set 2 that you're looking at, right? But let's look at the optimal growth model where the per period utility u of c is log c. And f of k is k to the alpha, where alpha is between 0 and 1. Right? So then the problem boils down to maximizing this discounted present value. And because of the log, this thing is not bounded, neither above nor below, because as things approach 0, the log shoots to negative infinity also. So there's neither an upper bound nor a lower bound, right? But notice that the feasible states, kt plus 1 feasible, right, is all states in this closed interval, right? So from 0 to the full output f of kt. But this full output now is kt to the alpha, right? So every kt plus 1 must be here, right? And therefore, log of kt plus 1 must be less than or equal to alpha log kt. But if you just iterate further, so log kt must be less than or equal to alpha log kt minus 1, less than or equal to alpha times alpha log kt minus 2, and so forth, right? So then you see that log of kt plus 1 is going to be bounded above by alpha to the t plus 1 times log of the capital stock that you started with. Yeah, so effectively there's a bound, see? If you look at returns in the current period t, f of kt plus 1, that's always going to be less than or equal to f of kt 0. So if you don't leave any capital stock for tomorrow and eat everything, your current returns will be the highest, right? But that's just log of kt to the alpha, right? Or alpha log kt, right? And if we do the iteration, this is less than or equal to alpha to the t plus 1 log k naught, right? So because of this, in particular, if I take a partial sum by multiplying both sides by beta to the t, right, then beta to the t f plus the positive part of this function, taking the partial sum and then taking limits as n tends to infinity. Here I have an alpha times alpha to the t beta to the t times absolute value log of k naught. That's just a geometric series and it converges here. So what that's saying is that this, where I'm just using the positive part of the function, is bounded above by this function of initial capital stock, right? So this will be true along any feasible path kt, right? Because of the constraint that is put on kt plus 1, that log kt plus 1 will be less than or equal to alpha log kt, right? So it will bound the feasible paths, therefore it will bound the discounted present value of returns, right? So the discounted present value of returns is always bounded above by that. And so we have this candidate value like function v hat that bounds everything from above. Okay? v hat of k being equal to alpha by 1 minus alpha beta log k. Right? It works as an upper bound. Does it satisfy the assumption t v hat is less than or equal to v hat? And we'll see that it indeed does. Apply t to it and you'll see that it does. Right? Right? So here we are applying t to the v hat function. Right? So t v hat of k is max across all feasible y's, that are y's between 0 and k to the alpha. Current reward, which is now, the utility function is the log function, log of current full output, k to the alpha, minus what capital stock I want to leave for tomorrow. So this is my consumption. Plus beta times v hat of y. Okay, v hat of y, remember, is this. Okay, so everything is nice and strictly concave, and I can do the maximization by a first order condition. So if I differentiate this with respect to y and set it equal to 0, in fact I get y is equal to alpha beta k to the alpha. So this max is equal to what I get if I replace the y's here with alpha beta k to the alpha. So I've done that here. And some simple manipulation will show that t v hat of k is just some c plus v hat of k, and alpha and beta strictly between 0 and 1 will show that this c term is negative. Okay, the c term is these two terms. So these are small enough that the log of these are sufficiently less than log 1, which is 0. So the c term is negative. So t v hat is less than or equal to v hat. Okay, and then we already know that t is monotone. So if we just iterate using t, we're going to converge to the v function that we want, right? And so we iteate first by, we have t v hat, use that as the value like function. Use that as the value like function to get t of t v hat, right? Do exactly the same exercise. You'll see that there are lots of constants and something which looks very similar to what you had earlier. Okay, so from the t v hat, there's the c term which will be a constant term, multiplied by beta. That won't affect the maximum value of y. The rest, the two terms, the rest of the terms are these two terms, log k to the alpha minus y plus alpha beta by 1 minus alpha beta log of y. That was there in the earlier iteration as well. So the max value in this special case turns out to be again y equals alpha beta k to the alpha. And if I put those here, you'll see that t2 v hat has this common term that t v hat also had, right? This term, these were in t v hat. In addition, it has a beta times this term. If we do t3 hat, t3 v hat, we'll have this term, this one, beta to the this, plus beta squared to the this, and so forth. So this is in fact a nice geometric series, and if you take limits, it'll just be this times 1 over 1 minus beta plus this, right? So that's my, by the theorem, that's in fact my value function v star. And you can also see that the optimal policy function here is this very simple function. Yeah. And I don't do discrete dynamics here in the deterministic case. We'll do some in the stochastic case. But if you do discrete dynamics here, you'll see that in this optimal growth model, the capital stock will converge to a steady state. And you can look at the figure that I've drawn for this.